Okay, so I think we can start. Thank you for being here today. Thank you to all speakers, to Mafalda Miranda. She's organizing this webinar today. I'm Daniela Blesend. I'm professor at Universidad de Medellín in Colombia, and I've been leading this IGCP 636 group since 2016. It is like a research network with several countries involved, several institutions, and we have been doing these webinars since 2022. This webinar is the last one for 2024. We are really grateful to this team from Portugal, all the researchers and professionals that are here today. The IGCP group, it's like a research group that just want to contribute to the diffusion about geothermal energy. So you can find all the recordings of these webinars in the YouTube channel. You can just look for IGCP 636, Geothermal Resources for Energy Transition in YouTube. And in a couple of days, you can find this recording and all the previous recordings from all the webinars that we have been doing since 2022. So I don't want to take more time. Thank you, Mafalda, all the speakers again. Mafalda, the floor is yours.
Thank you, Daniela. It's a pleasure to be here today with all of you to introduce this research group from Portugal that it's been very active on the research, development, and application of shallow geothermal systems. And this group has also developed a lot of research on this subject, but also on the design and the supervision and monitoring of several other projects in Portugal. So without further ado, I'm going to introduce our first speaker, which is Professor José Lapa. So Professor José Lapa is graduated in civil engineering from the University of Coimbra. He also has a master's degree in structural engineering from the University of Porto. Then he did a post-graduation in progressive collapse of structures at University College in London, and is currently a retired associate professor of the University of Aveiro. As you could see, he has a lot of experience, and is also a general director of Ferreira Lapa Limited, a private engineering and rehabilitation projects company in Aveiro. So, José, please, you can start sharing your knowledge with all of us.
Okay, thank you, Mafalda. Thank you, Daniela. Thank you for the invitation. Let me try to present. Okay, are you seeing my screen?
Yes, it's perfect.
Okay, thank you. So I will make an overview of this technology. We call it shallow geothermal energy systems. I made a collection of some information about our two countries, Portugal and Colombia. It's evident that we are different countries, so different climates, different population, different distribution of the population. So the question is we can put is that this technology is useful and usable in different country conditions. We can make this statement from our experience. Despite the multiplicity of social and economic circumstances of different climates, geology, and environment, this technology shows that it can adapt to any of the situations, depending only in its implementation because of different types of buildings and its energy needs. This shallow geothermal energy system is so-called very low enthalpy geothermal energy system because we are in the range of temperatures of the human body between 0 and 40 degrees Celsius. Um, this technology is for acclimatization of buildings, so as air conditioning of individual buildings and also for urban complexes, and realizing the following guidelines. The underground, so the soil in the underground, is a stable and endless source of renewable energy closer to the building. This closer to the building is important because normally the traditional electric power equipments uses energy that is transported from other locations. Here, in this technology, we use the energy close to the building, so the soil under the building, whose temperature is stable because it's normally between 15 19 degrees Celsius. This is already close to the human comfort range, which is around 20-25 degrees Celsius. The underground also is an excellent means of energy exchange. So we can easily, by using simple piping that we call probes, of water with glycol placed in buried structural elements or in geothermal boreholes or even in the horizontal collectors, we can exchange the energy between the soil and the internal space of the building. This transmission of thermal energy, that we call generally by heat, to the building allows the use of different forms through convection or conduction by air or water equipments, namely thermal convector, radiators, underfloor heating, vaporizers, heat exchangers in thermal active structures. So we have a different range of situations that we can transmit the energy from the soil, which is stable, to the building that is not stable because we have different stations of the year, summer, winter. So we can transmit this thermal energy and change the energy by means of geothermal heat pumps that can be used to correct and to transmit this energy from the soil. Uh, I mean the soil, but as exchanger mean, but we can use different other uh, changeable means, namely sewer, for instance, and air, of course, which is the normal uh, mean of exchange. But in this technology, we use normally the soil. About the efficiency of this technology, well, the efficiency is much more uh, interesting than the electric power because we can save a lot of electric power using the energy that the soil can offer. So we have efficiency in saving electric power, but we also have efficiency reducing the carbon dioxide emissions because this is a clean technology that do not produce any dust, any gas. So we can, by this means, reducing the carbon dioxide emissions. Also, the air quality and the human comfort of this technology, of this energy, the energy transmit to the human body, is quite comfort, and the quality of the air is not modified by any means of air uh, carbon dioxide emission, any dust, any gas. So the comfort is much more efficiency that the traditional ways of doing the transmission of energy. Also, I can use this in Portugal and the other countries that we know. This energy transmission is available without any fees or taxes. So there are no intermediate organizations, no uh, public interested in these kind of taxes or fees. Also, this means that the potential of this energy is quite sustainable. Also, we can include this urban distribution of cold or hot water in small neighborhoods and urban developments as we can use this to many buildings together. So the exchanging energy from the environment can be done by this means, by soil or air. So we have different kinds of transmission, and we can differentiate these technologies in four main groups of transmission. One is the usual transmission by air. So we can use air with not geothermal pumps, but usual pumps. Also by other means of conducting the temperature or the energy of the air to inside the buildings. We can call this the open air thermal system. The other one is using the soil, but using the water in the soil. We can use this in an open loop of transmission. We call this open vertical geothermal system. The other way, or the other main group, is using closed loop between the building and the soil, but at the surface of the soil. We can call this group as a closed horizontal geothermal system using collectors, or using the most efficient kind of transmission, that is a closed loop vertical geothermal system, which use probes inside of boreholes or inside of buried structural elements as energy piles. So these shallow geothermal systems perfectly use the soil as an external exchange medium, but we can use others that could do this transmission of the soil temperature or the water in the soil in the open loop, or using sewer, for instance. We can transmit this to the inside building, and if we have needs of cooling and heating, we can use reversible heat pumps that can be used to transmit not only heat but also cold energy for the interior of the buildings. These are some images from one of the buildings that we built in the University of Aveiro, using these probes inside the energy piles. We use energy piles because the soil here, the underground, is very soft. This is another kind of transmission of the energy from the soil, boreholes with probes, and this is machinery to make these boreholes. This main advantage is there is no need to transport energy between the different locations as the electric power, because we use the soil that are beneath the building to make this exchange of energy. Also, one of the more efficient ways of transmit the energy by conduction is to use the structure himself to do this transmission by using the tubes inside the slabs or walls. For instance, this is one of other buildings that we construct in the university or near the university. This one, which use the slabs to transmit the heating and cooling for the as a current hydraulic radiant floor, but using the inertia of the mass of the structure, this slab, that can contain the energy as cumulative equipment. So we can reserve energy to be released during the night, for instance, and prepare the environment for the next morning using this residual energy of the slab. The other ways are also conduction or convection by means of hydraulic radiant floors, UTAs, thermal convectors, radiators, and so on. So we use the usual means to transmit this energy from the soil to the building. Why the University of Aveiro became interested in this technology? The increase of population in our school between 2011 and the present time, you can see that we double in the 15 years, we double the population. This population is students, teachers, researchers, employees, postdoctoral researchers, and so on. So the needs of power, of energy, increases the cost of the energy in the university. So we are at the time challenged to use different technology than the traditional one that is normally chillers for cooling and other means for eating. So we search about solutions, and we find the solutions in the Central Europe for eating, but we also visit some buildings in Spain and check that also for cooling, this is a very suitable technology. So for our three main campus, which is Santiago campus, that I have 73 hectares and 49 buildings. The Castro campus that have 19 hectares and some buildings that are built in this second or secondary campus, and the other one is a creative science park. We call it PCI, which have 37 hectares. So altogether, we have about 66 buildings and 25 hectares of built area. So the challenge is reducing the energy demands of the buildings, the energy supply with minimal electric power use to achieve environmentally friendly acclimatization solutions, to achieve investment payback periods shorter than 10 years, and on less than 25% of investment in the climatization system when compared with the currently used electric power and gas-based solutions. What we offer as a solution is to have passive system solutions and concept to decrease the energy demand, to have geothermal very low enthalpy systems this technology. The use the conductivity of soils and to know where are the best soils and the best way to achieve the energy from the soil. So the conductivity of soils and rocks, we made some research to have some realistic values of the ground energy potential. The building and geo exchanger system with water reversible heat pumps, to use collectors on boreholes or on energy pile systems, to use sewer as another kind of exchange in for the thermal exchange of energy. We call it geothermal energy. Thermal active building systems with acquisition of concrete slabs. On the slabs, we put the probes or the exchangers to transmit to the mass of the slab concrete, and then this way to have more efficient transmission of the energy to the building, and also to use phase change material PCMs used to heat or cooling energy storage. This way we start in the 2011 and until the COVID time, until 2020, we built 6 buildings in the university, and this way we have some sort of knowledge to understand the design, to understand how we can put the exchangers, many things about problems of this technology. After the COVID, we also make some studies and projects and of private buildings as offices, services, hotels, rehabilitation, industry, senior residences, and healthcare buildings. And this way, we have some knowledge about how to design, how to build, and how to use the different technologies associated to this main technology. This is some examples, images of one of the buildings that we made in the main campus, Santiago. These are energy piles. These are an exchanger of sewer. The sewer is exactly as the soil. It's the bin that we use to exchange energy. But here in the sewer, we use a main tube that have around 25 to 28 degrees Celsius, which allow us to use less electricity to the same energy that we want to transmit. These are valve boxes. This is the circuits in the slabs. So we use here the exchangers inside the slabs. This is the room where we have the heat pumps and the circulation pumps, and here is the electric box, and we use only a small PC to use software that manage all the system. This is the software here. So in any time, we can see what is the temperature in each room, or in the corridors, or in the amphitheater. And we also have the input, the inside temperature, and the temperature in the some of the boreholes and in some of the energy piles that we have monitored. This is a sort of different drawings that is the project of this building. Here we have a diagram, the principal diagram of the system with the primary circuit and the thermal power station. Here we have the outdoor geothermal system and the thermal power plant. Here it's some circuits in the slabs in the building, and here it's the secondary distribution circuits of aerobic networks, because together with this system we need some sort of ventilation, which is very necessary in this technology. So we use aerobic networks also conditioned by this temperature that we change from the soil. Also, we have some instrumentation to collect some data. Also, we have some research on these buildings, some continuous data collection that we can show you in the next presentations. And these buildings are normally the same type of buildings here in the university. The gross construction area is about 4,500 square meters. The deployment area, it's about 1,600 square meters, and the air conditioner usable area is about 3,500 square meters. For this building, we estimate the needs for this building 134 kilowatts hour for heating and 152 kilowatts hour in cooling. The geothermal system and biothermal systems, we have two systems in this building, are 55 energy piles of 600 millimeters diameter and 30 4,000 millimeters, 400 millimeters diameter. Also, we use that biothermal system when one stainless steel exchanger of 350 millimeters diameter with three exchangers, which gives 3 by 32 meters long exchangers. And the installed power of these two systems, the first one from the soil, 100 kilowatts hour of heating, in the heating, and 90 kilowatts hour in the cooling. So the cooling is not covered by this one, and we need the second system to have the needs covered. Also, we use this TAP solution, thermal activated building system, with two geothermal heat pumps, two buffer tanks, and for compensate the system and to use it as domestic hot water. 10 circulation pumps and the heat exchangers in the prefabricated lightweight slabs of honeycomb panels. Because we put the exchangers on the top surface of the slabs, it reveals very low efficiency. So for this top solution, we need a more complete concrete solutions as concrete slabs. Some financial evaluation of the system, because we present this solution in inside these limits of the university, namely 25% of investment, and being limited also by the cost of the maintenance and the energy cost. So we compare our data from the consumption of the energy in the energy during 7 years, with comparing this with the what we consume if the solution is the traditional one, with electric energy and natural gas. So we compare this, and the investment cost is a little bit more than the traditional one. It's around 6 or 7% more, but the annual maintenance is 3 times less, and the energy annual cost is also 3 times less. So in almost 7 years, we have paid the investment. So payback period is around 7 years. So really, from this building and the others, we can resume this as the investment, the initial investment. Um, it's around 3 or 4 times, um, three or four or more 7% of more than the investment in the traditional system, but we can gain 45% in the energy consumption in heating, and almost 70% reduction in the energy consumption in cooling. So the expectation for residential and services building, not in the single residential or family residential buildings, not for that. We can expect about 7 years payback. There are many others buildings with this technology. We can show you some hotels, resorts and spas, some senior residence, and a big complex in Lisbon, made by this insurance group, Fidelidade, which is around 45,000 square meters construction, this building. And here we have 4 buildings of more or less 90,000 square meters, all with this kind of technology. Also, we can use this in the urban complex. For instance, this tourist development in the south of Portugal, we call it Algarve. Probably you know these places. And also in the industrial equipment. For instance, this facility, which is only cooling system of industrial equipment. They have another kind of solution, and this is the recording of that system. It's an air-to-water chillers, and the power consumption of that solution is about 400 kilowatts per hour. And with the geothermal system, we see a significant reduction to 67 kilowatts per hour. So the financial return or payback return was around 2 years. Another one, also a complex and an industrial complex, but the administrative services of that industry. They have another one that consumes around 380 kilowatts hour, and this administrative services, a new building, consume around 60. So in 2 years and 6 months, the investment is paid. About the future, this solution can be constructed together with others, namely solar panels, another kind of for instance, wind solutions, cooling towers, and so on. So we can use this technology together with other renewable energies coming from the air, the water, or the sun. And together with the passive sources of solar energy, advanced material as PCMs, thermal insulation, buried pipes, daylighting design, passive cooling. So with these passive sources, together with these active systems, I think we can have a very good, efficient, and sustainable energy for buildings and for urban complex. Well, thank you very much.
Thank you, Jose. Was an amazing presentation. So now I'm gonna introduce our next speaker. So next we have Dr. Ana Vieira. Ana is a senior researcher in the Geotechnics department of the National Laboratory for Civil Engineering, and has a PhD in civil engineering from the University of Coimbra, and has participated in and coordinated several research projects within the national lab, and has also done several other contract research studies and specialized technical consulting. She's president of the Portuguese Committee of Environmental Geotechnics since 2020, co-author of the Soils and Rocks Journal since 2021, and until 2020, she was Secretary General of the Portuguese Society of Geotechnics, and this short bio gives you an overview of the amazing work that Ana has been doing. So Ana, the floor is yours.
Okay, thank you, Mafalda, for this kind introduction. So I'm going to start by sharing. Okay, it's okay? It's on?
Yes.
Okay. Good morning or good afternoon, whatever is the case. First, I'd like to acknowledge this kind of invitation to participate in this interesting series of webinars from the UNESCO. Let me see if I'm going to spell it right. IGCP 636. It's really a pleasure to be here. I thank again Mafalda for providing this connection, okay, and to Daniela for this for believing in us and inviting us to share the experience that we are developing in Portugal in the aim of shallow geothermal energy systems. So I'm going to talk a little bit about the external context and on the ongoing research of shallow geothermal energy structures in Portugal. So, of course, it's almost imperative to talk a little bit about the climatic context. It's determining all of this increasing attention that is paid, for instance, not only to geothermal energy systems, but also to every green energy source, which enables, in some manner, to mitigate the impact of human activity in the environment. And regarding the geothermal energy systems, as my colleague before showed some very interesting and promising numbers, the experience is showing more and more that the use of this resource that is available in a continuous manner has to rise, and we are working on that. We believe we are doing our part in research. So these are some aspects that I took from the IPCC website. So there is no doubt climate change is affecting the human life, and these are some of the main points we are all experiencing. The rising of global temperatures, the melting ice, and the rising of sea levels, extreme weather events. During the last week, there are a lot happening, for instance, in Europe. The changes in ocean, namely the temperature of the water, of ocean water, the impact on biodiversity, and of course we have the economic and social consequences, and the need to take global actions and policy and adequate policy measures, and of course the importance of technological innovations. The IPCC has released a very interesting report, a synthesis report on climate change in 2023, and my advice is for everyone who is interested, not only academic, but for the public in general, to read this report and to really be aware of what is going on and what is happening in terms of climate change. So I'm not going to read all of this, but of course there are a lot of aspects that we are all feeling every day and reading, and we have to do our part. And also in IPCC, when this report was released, there was also a press release which dictates that there is a need to take urgent climate action in order to secure a livable future for all. There is still time. There are multiple and feasible and effective options to reduce green emissions and to adapt human to climate change, to mitigate and to reduce the impact of climate change. So there is an increasingly narrow window of opportunity, but let's take this opportunity and produce a climate resilient development and improve our quality of living of the actual societies. So we are not only talking in climate, we are also talking about the energy context, of course, with the increase of population. There is and also a parallel increase in the needs of energy, and to make a bridge with climate. There are a lot of reports here in the group of the United Nations Climate Action. I took this picture of 3 very recent reports. They work very intensively and these reports give a very good overview of what is going on. I took some aspects of the resourcing of the energy transition. So we have to work all together to promote energy transition, to decarbonize the environment. So I took also some charts that I think that are very elucidative of IEA, International Energy Agency. Here in the left shows the huge increase in the energy in electricity generation in the last 30 years or so. And coal, fossil fuels are still in the lead and in a large manner, I'd say. However, very recently we show an increase in the use of renewable energies. Here, wind. However, geothermal is still not on top, but we think that will be because there is, as I said before, an increasing interest in the use of geothermal energy. Also here in the on the right, some trends. For instance, the global investment in clean energy technologies, it is worldwide. In the last 2 years, 2022, 2023, in blue, we have the clean energy sources, and the increase, the rate of increase is really interesting and it's promising, I would say. And here in the bottom right, some provisions from 2023 to 2050. So the goal or it's desirable to get an almost balance in the energy production available from clean sources and from fossil fuels. So let's believe that we are still on time to reduce. Okay, I'm being positive, but I'm not sure if things will go so well. But let's hope so. And here I took also the pictures of 2 very recent reports: the State of Climate, an update for the COP29. I believe it has ended some days ago. And another report from the International Energy Agency, of which are the perspectives for the energy technology. So there are a lot of things that are working not only in geothermal systems, but in a lot of sources of energy in order to use technology to promote a better future for us all. So, and which is the role of shallow geothermal energy in the environmental protection? I believe that Lapa has already gave a very good overview with the Aveiro case, and not only, but as we saw before, as I mentioned before, the CO2 emissions from the burning fuels are one of the greatest challenges of our century. And we are looking for renewable energy solutions in order to mitigate climate change. Shallow geothermal energy emerges as a very promising alternative, and it's becoming, as I said before, more and more used, as it uses cleaner renewable energy source. It's not an infinite source, but is a direct and easy to use. We need to adapt and to use it in a more current way. So here is a picture not only of shallow geothermal systems. In shallow geothermal systems, I have to say that we are not producing energy. We are using directly the thermal energy from the shallow soil layers in order to heat buildings, to cool buildings, or to store thermal energy, among other applications, but these are the most frequent. I took also this fact sheet from a European research project that is mused, and this fact sheet gives in a very condensed form a lot of numbers and informations and about of forms in which shallow geothermal energy can be used, as I said, in thermal storage, it can be used in vertical or horizontal borehole exchanges. It can be used in the foundations, in piles, in slabs, in retaining walls. They're usually called thermoactive geostructures. Another promising way is to use the excess heat in the industry for and to store this energy in order to heat spaces in buildings and but not only to heat in domestic waters, for instance. And if it is used in a very systematic and current way, of course, that the savings in energy and the reducing in CO2 emissions can be very, very interesting. So, of course, in urban space, in urban areas, we have around 64% of the world primary energy consumption. So, of course, that cities are in the focus of our interest and of our study. Not only cities, but they are the most well, it's where the energy is needed the most. So here are some numbers. I invite you to also to consult this Muse fact sheet. It's a very interesting research project that is underway. So now I'm going to talk a little bit about our research. We have been working with the Aveiro University for 10 years from now. Actually, this cooperation began when I saw a presentation of José Lapa in a conference, and he showed the example of Aveiro, and I was very enthusiastic and very happy to know that in Portugal there were a series of buildings that were actually using the shallow geothermal energy. In LINEC in Geotechnics department, together with some colleagues, had been working in soil thermal characterization. So I have a meeting with Lapa. Oh, it's very good. You have the building. We have some knowledge in thermal characterization. So let's join our expertises, and you have the prototype, the building, and let's try to run for a research project. And we did, and the project was succeeded, and the project acronym is SUCCESS, and the title is here: Sustainability of Shallow Geothermal Systems, Studies Applied to Southern European Climates. So it ran for 3 years, from 2016 to 2019. We can't also with the participation from Lisbon Technical University, and I should say that this project was a very, very successful one. This is almost a repetition, but okay. The goal of the project was to analyze in an integrated manner the parties involved in the building equipped with a ground source heat pump system, the shallow geothermal system, and reproduce its overall behavior. So we have the building monitored, we have the soil characterized and monitored, and we assess and study the two systems, which are usually known as the primary circuit and the secondary circuit, and study the overall functioning of the system in terms of energy exchanges, and not only, but one of the main points was that, and to assess if the system is sustainable or not in a lot of features. So here is the structure of the project. It was divided in 5 tasks: lab, characterization, in situ soil sampling, numerical modeling of the system, integrated analysis like cycle analysis, and energy efficiency analysis. Later on, we have gained a lot of expertise. We made a lot of tests, thermal tests to characterize the soils, Aveiro soils, in terms of thermal conductivity, heat capacity, etc. We have monitored the soil. There is a monitoring system that is still working. We measure the impact of the exploration of the shallow geothermal system. And based on all this experience, we invited Lisbon municipality to join us in another project. And we have the agreement of Lisbon municipality, and we got funded for another project. That is Project of Sustain, that is still running. So the title of this project is Sustainability Assessment of Shallow Geothermal Systems for Lisbon, Characterization Studies of the Soil, of the city soil's thermal and thermomechanical behavior. At the moment, as Raj will, in the last presentation of this webinar, will provide you more information of the soil tests that we are carrying out in Lisbon. There was no information about the thermal properties of the soils in Lisbon, and Lisbon is a very interesting and very complex city in terms of geology, and we are trying to give some information and some development in this topic in order to provide the city with a thermal mapping and the zonation in order to use and to facilitate the use now and in the future of geothermal systems. So the main objective of the project is to provide an applied and fundamental research to support sustainable planning with significant relevance to society in adapting climate change. So also with this project, we have 4 consultants, and we have been producing a lot, and we've been also in the interest of various different institutions and colleagues. So we have been working very much. Some of the work Lapa has showed, and the 2 colleagues will also show some of the results that direct or indirectly also result from this project. So this project actually is an improved version of the first, much more ambitious, and it's divided in 6 tasks. Here shown: task 1, field work, soil sampling and temperature profile monitoring, system installation. It is already been carried out. At the moment, as I said, we are characterizing the soils in terms of thermomechanical properties. This is the first time that I mentioned thermomechanical, but we are also studying the effect of temperature, not only in conductivity, but also in the mechanical performance of soils. How do the heat cycles, the permanent heat cycles with increasing temperature affect the formability and the strength of soils, and how it would impact in infrastructures. So we are beginning to do this study. The study is beginning, but there is a lot of things to do, of course. We have also task on numerical simulation with advanced constitutive models. And task 4, the compilation of geological and geotechnical and thermal characterization that different scales is running. Also this task, the sustainability of the systems for Lisbon soil and climate conditions. Some work has been done, and more work has still to be performed. We are also carrying out integrated analysis, and we have a global task of the dissemination and and promotion of the results and of communication of results of the project. It is also one of our objectives, of course, to keep the technical and scientific communities aware of what we are doing. We had already 3 public events of GeoSustain project, and we will have a 4th at the end of the project. So, of course, we are aligned with the United Nations Sustainable Development Goals, namely with Goal 7, ensure access to affordable, reliable, sustainable and modern energy for all. Goal 9, build resilient infrastructure, promote inclusive and sustainable industrialization and foster innovation. And also with Goal 13, take urgent action to combat climate change and its impacts. This is our team, and now I'm going to go for another project now involving foreign institutions. So recently, this project that we had with Aveiro University and LNEC, we had with the partnership of the University of Stavanger. It was also a very interesting project, and more things will happen following this. And the title of this project was Store to Sustain, and it addresses the shallow geothermal energy system integration with underground thermal energy storage for sustainable heating and cooling. So here, the novelty is that we address the topic of thermal energy storage. Again, the integrated building and shallow energy system analysis. Another topic is the urban district heating, not only in isolated building or infrastructure, but at the level of the district. Other projects that in which we are involved. In LNEC, we have the E2I Research and Innovation Research and Innovation Strategy for LNEC from 2023 to 2013. Of course, this shallow geothermal energy is completely aligned with this, namely the topic of society intervention priorities defined in national programs, Portugal 2013, areas of action defined in European programs, Horizon Europe and the European Green Deal, the United Nations Sustainable Development Goals, as I mentioned before. The topic is also aligned with the Geotechnics Department research lines, namely here in this topic, sustainability and resilience of geotechnical structures. We in LNEC and also colleagues of Aveiro have also been part of 2 cost actions. Cost actions are European programs, cooperation for science, research and development. This CA 18219 has ended this year. It addresses the research network for including geothermal technologies into the carbonized heating and cooling grids at the district level. And there is another action that is still running. It has around 27 countries or something involved. And the title is European Network for Fostering Large-Scale Implementation of Energy Geostructures, acronym FOLIAGE. We are around in the midterm of the project. So the project will end it in 2026. Now, very briefly, some results. We have been working for some years in thermal characterization we made the thermal tests using different sensors in samples retrieved from different locations and at different depths. The study of thermal conductivity is crucial. It's crucial for sustainable and well-designed shallow geothermal energy systems. And from one formation to other, thermal conductivity can vary significantly. So it's important to access this parameter in a proper way. We have also carried out 2D and 3D models in order to complement the studies in lab. We have also tested and reproduced numerically a lot of tests and analyzed the effects of several parameters. For instance, the duration of a thermal test, how much time should a thermal test take in order to have a good results, the importance of the conductance and the resistance between the needle and the recipient and the soil. There are a lot of things that affect thermal conductivity measurements in lab. We are also devoted some a lot of work in this topic. It's also in our focus of interest. And here I show some results of GeoSustain project. In the center, a map of thermal conductivity of the surface, the formations in Lisbon. So it was the first time that such a map was produced. At the moment, we are, as I said more than once before, we are complementing this information with thermal tests at different depths, not only at the surface, of course. More important than at surface are the thermal conductivity in depth in order to design the systems. So we are carrying out multi-scale thermal characterization. We are also using the database available in the city council of boreholes that are here with this huge amount of dots, and we are crossing this geotechnical information, and with this geotechnical information we are also giving some perspective of some estimate of the soil thermal properties. Thermomechanical tests, as I told you. We have an automated triaxial environmental system. So we are going to do very briefly to study the effect of temperature in the formability and strength of soils in order to accurately predict the performance of infrastructures in the future, and how, for instance, the heat waves could affect the performance of the systems. Also, here are some pictures of the results of the implementation of thermomechanical models that are being produced by two colleagues, mainly by two colleagues of the geotechnical department that are really experts in implemented advanced constitutive soil models. Also, here are also some pictures of the numerical models. Okay, we have to characterize the ground properly and the building in order to have a good estimate of the energy exchange and on the impact of the geothermal systems in the long term, in the short and also in the long term. And a lot of things have to be integrated in this analysis. And this is a picture of a very recent PhD thesis that was completed also in the aim of the project. And the case study is Aveiro University building here as a prototype, as I told you before. The building was modeled with Energy Plus software. The ground was also modeled, and all the energy exchanges were modeled based on the on the climate and on the soil conditions and the energy needs of the building. And we have a lot of outputs and sustainable indicators. First, we use the local data, of temperature in Aveiro City. Then we make some extrapolations of some studies considering if supposing that the building was constructed in another city in Portugal, Lisbon, Porto, etc. So the impact of the shallow geothermal energy system under these different climate conditions was also studied, and there is a lot of things to do following it. A lot of things were done, and a lot of things, much more things are to do in this topic of integrated analysis. So here I show some results of, this is the same building. In this building, a lot of sensors are placed in different boreholes, temperature sensors, and the temperature is being monitored in order to assess the influence of the exploitation of the geothermal system. Does the geothermal system impacts with the field, the temperature field during time? Is this impact important? So in the long term, it is possible. We have I believe that around 4 years of monitoring, so it's not much, but we'll have more. And with this data, there is a huge amount of data, and with this data, we can try to understand which is the impact of the exploration of the geothermal system, taking into account also the influence of the variation of the atmospheric temperature. And this 4-year data, we have make some analysis, and the impact, we are still treating the data because the temperature increased, but the atmospheric temperature also increased. So we are trying to correlate the effects of all these factors interacting together. This is what I was showing, what I was told you before. These are heat maps from from 4 boreholes. We have 19 boreholes being monitored. I show here 4 boreholes, and we, as I told you, we noticed in the surface an increase in temperature, but it is not still possible to isolate the effect of the geothermal system from the effect of the atmospheric temperature that has really increased significantly in this 4 years. So I would say that the time, the data is still very short, 4 years, but in the coming years, and with proper machine learning and other artificial intelligence techniques, maybe we'll be able to understand more and more what is going on. In Lisbon, we are also measuring temperatures in depth, and here are some pictures of the installation of a system. In the right, we have the map of Lisbon, and in Lisbon we have around I would say half a year of temperature monitoring till 80 meters, something like that. And it's also the first time that we have continuous temperature monitoring in Lisbon till such high depths. So I believe this is the last slide. Thank you very much.
Thank you, Anna. Thank you so much for your presentation. So I'm going to introduce the next speaker. So Antonio Figueiredo is assistant researcher at Risco Research Unit in the Department of Civil Engineering at the University of Aveiro. Antonio is author and co-author of more than 60 publications, and his research aims to contribute for the development of a sustainable and resilient building stock, particularly related to climate change, well-being, and energy efficiency, introducing and promoting geothermal energy systems and renewable sources, and use of evolutionary algorithms for optimal building design. So I am looking forward to hear what you have to say, Antonio, but I kindly ask if you can keep it short because we are running out of time.
Okay. Hello everyone. Mafalda, thank you so much for introducing me. Well, I will try to be really fast in this presentation, just to give an overall view of the work that I have been done. Well, and today I will speak about the monitoring, modeling, and the building energy analysis. I will start with monitoring, then I will talk about modeling, about dynamic simulation, the tools to perform the design, and then a short, small presentation regarding the energy and thermal comfort analysis. Well, in this presentation, I will focus on the CCCI building. It was the last school building to be built in our university. This building consists of one underground floor for technical areas and 3 upper floors, elevated floors. It has a regular shape with a total in width of 20 meters and a length of 80 meters, just to have an idea of the dimensions of this building. Well, in relation to geothermal system, 42 thermo-activated boreholes with a diameter of 160 millimeters was installed in the building with a vertical pipe with a diameter of 40 millimeters, and the boreholes has a total of 104 meters deep. In the next slides, well, we'll see in detail how geothermal system was installed regarding the monitoring in the exterior part of the building and also in indoor conditions. Well, regarding the monitoring, as I said, this presentation is divided in 2 main points. The first one corresponds to the monitoring of the exterior part of the building, and the second one corresponds to the interior part of the building. Okay, so regarding the exterior part, and she already speak a little about this topic. Well, PT 100 probes were used to measure and to record the temperature in deep in the boreholes. The monitoring plan shows geothermal boreholes in black. We could observe here. I don't know if you could observe my mouse, the mouse position, I think yes. And the blue one corresponds only to boreholes that was used just for research purpose, okay? They are not exploring or they are not being exploring in terms of energy, in terms of heating or of heating extraction or cooling rejections. And the other two, these two with the red color, well, the probes were placed in these two tests and to also check the heat exchange into energy piles, okay? In terms of results, I would like just to highlight a couple of main conclusions. Well, and if we look to the right plot in the right part of this presentation slide, well, the seasons influence the temperature up to a deep of 10 meters, okay? And at a deep of 15 meters, we could observe in the red line, not in red, the green line and this yellow one, that a constant temperature of 16 degrees was attained during all the year. And if we look to the other plots on the left side of the slide, well, the influence of weather on temperature is visible just only to 10 meters, as I said before. And after this dip, well, the temperature is almost constant with a delta T of 3 degrees regarding the maximum and the minimum temperature attained in one borehole. Okay. Now moving on to the monitoring of the interior part of the building. Well, three main characteristics were measured and monitored: power and energy to obtain the internal loads of the building. This is paramount as input for the building energy modeling and also for validation purposes. And the temperature was measured with the portable data loggers. All the thermal zones were monitored with several points well, to have a complete full data regarding this perimeter in all the building, all the zones orientations regarding south, north, east, and west. Well, every thermal zones with different properties were installed this kind of sensors and monitored for more than 1 year. The power and energy was also measured, not so long time, but during almost 3 months. In terms of air leakage, and this is the third parameter that we did a lot of tests, because the air leakage of the building has a high impact on the thermal and also on the energy consumption. And to perform these tests, blower door tests was used individually in rooms, in specific rooms, to check the air permeability of the windows, of the frames of the windows, and also an overall test in all building was also performed using two equipments, two blower door tests to measure all the building during one test. Well, looking for the results with the monitoring data, is possible to characterize the building in terms of thermal performance. And we could observe that there are a lot of points in discomfort. But if we analyze in detail, a lot of this data was occurred during the night, because in the first times the system was turned off during the night. And everyone knows that this kind of systems is designed to be always working during the day and during the night to have a constant temperature inside the building. In terms of energy consumption, well, the auditorium stands out as the thermal zone with the highest consumption in the building. And well, it is because this specific thermal zone has, well, high ceilings, and this zone, it has a really huge dynamic behaviors in terms of occupation. Moving on to, well, to the second part of this presentation, in which I will focus on dynamic simulation issues. Well, I would like to start by pointing out the need to numerical model calibrations, because currently we are designing our buildings using steady state methods that they don't reproduce the real behavior of the building. And using steady state methods, well, there are a lot of uncertainties in our models regarding geometry, the materials, the equipment, the lighting, the windows, the ventilation, of course, and especially the user actions. Okay, the users has a huge influence in the performance of the building. So we have all the facilities, all the computers. Well, we have all the ingredients to go further to dynamic methods. And with a dynamic approach, it is possible to reduce the uncertainty regarding all these parameters that has a huge influence in the performance of the building. We could create specific schedules for user actions, okay, to reduce, well, the problem, the issue of the steady state methods. And if we want, well, it is possible to go further because we already have all the tools to easily develop an optimization process to reduce our level of uncertainties as much as possible, to design solutions that are really accurate with the real behavior of the buildings. And in an optimization process, we could instruct our software, in this case, the Energy Plus software was used. Well, we could create a routine to instruct the software to give us the best results by changing, for example, predefined parameters. In this specific case, we use an evolutionary algorithm to instruct the Energy Plus and to find, and finally, the MATLAB to get the best results, well, that we call as Pareto front. Now moving on to the case study, and I start by doing a question, and the question is how to improve the ground heat exchanger efficiency. Well, in this case, of course, that we use the dynamic simulation. The model firstly was calibrated using real data, okay? And then the performance of the building was evaluated by changing predefined parameters, okay, of the geothermal system. And then an evaluation was performed in terms of energy and in terms of thermal comfort by changing all of these parameters. In terms of goals, there are two main goals. The first one is to attain improved performance of the building, do the characterizing each parameter individually, and then attain improved performance of the building by combining different parameters through the development of a parametric combination. And the parameters are listed here at the left part of the slides. The reference value corresponds to the real data that was obtained under real conditions. Okay, this, for example, this 16 degrees in the ground temperature was the temperature in average of the boreholes that we collected during 1 year. And then in the parametric values, we tested different values, for example, 15 or 17 or 18 degrees in these specific parameters, okay? And the similar process was performed for all these 9 parameters that we are listing here at this table. Regarding the methodology, well, the building geometry was defined with the SketchUp software, and then some main properties, such as properties of the walls, regarding thermal properties, U value, the slabs, the glazing, the G value of the glazing, the occupancy, the schedules. Well, were defined in the Open Studio, and finally the simulations were carried out in Energy Plus. And this plot represents the energy demand of the building, the energy needs, okay, in terms of cooling and in terms of heating. And we could observe that, well, there are a lot, or there are more needs in terms of cooling instead of heating for this specific type of building. After we have simulated building needs, we moved on to design of the geothermal system characteristics. And in this case, we use the software IGCHP to simulate and to test all the parameters regarding the system, regarding the boreholes, regarding the heating pumps. Everything was simulated into this software. Moving on to the results, and just as example, for this building, the increase in temperature leads to an increase in the energy consumption for the total energy consumption. And when I'm talking, when I spoke about temperature, I spoke or it regards the temperature in the middle part of the boreholes, and it represents an average of all the deeps that we have monitored, okay? Another example, in this case, we considered the borehole radius. And in this case, well, a similar behavior was observed with the borehole radius increase. Well, the energy consumption of all the system was also increased. In the parametric analysis, 3 parameters were changed simultaneously. In this case, the ground temperature, the U-tube size, and the ground thermal conductivity. And the results shows that for the minimum energy consumption, well, the ground temperature should be 14 degrees in this case. The U-tube size, well, the best results were attained with a U-tube size of 32 millimeters, and the ground temperature conductivity in the maximum value possible, 3.2 watt per meter per degree. Well, just some final remarks about this work. Well, the energy consumption decreases when the borehole radius decreases, when the ground temperature also decreases, but for example, the energy consumption decreases when the ground thermal conductivity increases, and also the grout and the ground thermal conductivity. Well, dynamic simulations was revealed as a needed tool for an accurate system design, and use of geothermal system as a renewable and sustainable energy technology should be incentivized towards building more energy efficiency and even environmental friendly. Well, thank you, and I give you the word to my colleague.
Thank you, Antonio. Thank you so much for your presentation. So right now, we're going to move on to our last speaker of this webinar. So I have the pleasure of introducing to you Rajendra Roca. He's a PhD candidate at the University of Aveiro from Portugal, and he's originally from Nepal. He holds a master's degree in environmental engineering and a bachelor's degree in civil engineering. Since July 2023, Rajendra has been conducting an internship at the National Laboratory for Civil Engineering in Lisbon, and his doctoral research focused on soil thermal characterization to optimize the use of shallow geothermal energy for building energy simulations at both building and urban scales. He aims to advance sustainable and energy-efficient building designs through innovative geothermal solutions. Rajendra, please go ahead, and if you can keep it short, I will very much appreciate it.
Okay. Thank you, Mafalda. Do you see my screen?
Yes.
Okay. So good afternoon, everyone. I'm going to make it very short. I'm going to present my research on the thermal characterization of soil and the use of shallow geothermal energy system for improving building energy efficiency. My work aims to contribute to sustainable energy solution in the context of building energy. The operation of building account for around 40% of global final energy consumption and around 26% of global energy-related emissions. So almost half of the energy demand in the buildings was for the space heating and cooling. And to mitigate the problems, we can use the geothermal heat, geothermal energy. In our case, we'll go for up to 150 meter deep to retrieve the energy, heat energy, about 10 to 30 degrees centigrade. For my thesis, I have two objectives of my research. First one is to characterize the thermal properties of soil in Aveiro and Lisbon region of Portugal. This involves assessing the physical, mineralogical, and thermal parameters of various soil samples. And the second one is to evaluate and enhance building energy efficiency using shallow geothermal system. This will be achieved through the detailed multi-scale modeling, which integrates shallow geothermal system into building energy simulation. These are two distinct regions of the Portugal, which are climatically and geographically distinct, and they have different soil types as well. And moving to the next, I will go for the whole building energy simulation of CCCI building. I will be used as a calibration model for this because this building is already equipped with the shallow geothermal system. And then I will go for the whole campus building simulation using the shallow geothermal system in urban scale. Despite the advantage of shallow geothermal energy, its widespread dissemination faces several challenges. So these include a limited understanding of subsurface thermal properties, high initial investment cost, legislation, land use, land occupation, public governance, and subsurface structures. So my research focus on addressing one of the dominant barrier by providing detailed soil thermal characterization and demonstrating the benefits of integrating geothermal system in building energy design. This slide shows the location where the soil, we took the soil samples, or we collected the soil samples in Lisbon. We choose three sites where we drilled 3 boreholes up to 80 meters and 2 construction sites. And in Aveiro, we choose 1 construction site and we retrieve the sample up to 3 to 3.5 meter. And here are some glimpses of disturbed and undisturbed samples that we retrieved from the locations, sampling locations. In Lisbon, as a part of GeoSustain project, we used the drill rig of FD 1200 SD NCB with the drilling capacity of 104 kilowatt. and the sampler having length 1.9 meter and diameter of 68 mm. To retrieve the sample from Aveiro, we use the metallic tube of length 140 mm and diameter of 70 mm. So for the purpose, we conducted several tests to assess the soil physical characteristics on the collected soil samples, including grain size distribution, particle density, water content, void ratio, and degree of saturation. And the test helped to classify the soil and provide a basis for understanding its behavior. Knowing the physical properties is essential for predicting how the soil will respond to thermal changes, which is critical for the design of geothermal system. Here are some glimpses of the tested samples. As we can see that the different soils from Aveiro and Lisbon, they are different in appearances, and they are different physical and mineralogical properties as well. Here are the thermal probes that we use for the thermal characterization of the soil samples. We use three thermal probes. The two are the transient line source, and one is the transient plane source. The first one, TLS 100 VCP, as we see here, that can measure thermal conductivity, thermal diffusivity, and volumetric heat capacity simultaneously. So we can see in the table we have different properties of the thermal probes. Here comes the result of the physical properties that from the soil from Aveiro and Lisbon. As we see here, we have different soil properties, like the degree of saturation ranges from 29 to up to 98, almost fully saturated. And the void ratio ranges from 0.3 to 0.8. And if we see here, the Lisbon soil doesn't have the gravel content like this. So here we developed the particle size distribution curve, which demonstrate the variability of the soil types in Aveiro and Lisbon, and that is very important. To analyze its effect on the soil thermal characteristics. Here is the result of the thermal characterization with the three thermal probes. We see here the Aveiro soils have consistently higher thermal conductivity values than the Lisbon soils. And as you see here, the transient plane source, they are also giving lesser values than the other two thermal probes. So the result indicate significant variability, highlighting the importance of selecting appropriate measurement techniques and understanding local soil characteristics when designing the geothermal system. Here we see the result, the analysis of water content versus thermal conductivity. So we see here, we observe here a strong positive correlation indicating that as water content increases, the thermal conductivity also increases. This is because water being more thermally conductive than air, that enhances water heat transfer in the soil. As you see here, when the air gap is filled with water, then the thermal conductivity will be increased. The graph is developed by the series of thermal conductivity test with the needle probe, and in each test the soil tends to lose the water content. So after every test, we see that the thermal conductivity value also decreases. Here we see the graph of degree of saturation versus thermal conductivity. In the right side, we can see that the thermal the general trend of the thermal conductivity with the degree of saturation. As we expected, the general trend has increased with the increase of the degree of saturation. But in the second, in the left side, we see here also when the thermal when the degree of saturation increase, the thermal conductivity also increase. But when we analyzing sample by sample here, we can see in the sample 6078 and 6089, even though degree of saturation is higher in the 6089, the thermal conductivity is quite low. It is because, yes, of course, the degree of saturation helps to increase the thermal conductivity, but it is not only the sole properties, physical property that governs the thermal conductivity. So it is thermal conductivity is very complex to analyze. So we have to go to the mineralogical analysis and other relation with the other thermal other physical properties as well. Here we see the void ratio versus thermal conductivity, and the general trend is like when void ratio increases, the thermal conductivity decreases. As the void on the soil increases, the thermal conductivity decreases because of the low conductivity of the year. And in the left side, we see if we analyze the sample by sample, the 6061 sample has very high void ratio and low thermal conductivity. Here we have the density versus thermal conductivity. Also, as expected, the thermal conductivity increases with the increase in the density because the contact between the particles increases. So we also analyzes the mineralogical contents of the soil. We have here is only one the result from the only one sample, but we still waiting for the result from another samples. However, we can see here the soil contains 63.7% of quartz, and we can expect that this soil has a higher conductivity than other soil because it hides a high quartz content, and the quartz hides the very high thermal conductivity. Moving to the next objectives, I will go for the building energy simulation for the CCCI building. As I mentioned before, I will use it as for the calibration purposes, and I will go for the whole campus building simulation. For that purpose, I'll use the SketchUp model for 3D modeling, and I will import it into the CitySim Pro model for the whole building energy simulation. For that purpose, I will adopt the climate data from the metronome, and I will use the real physical data from the building data and occupancy data, and I will simulate the whole buildings for the purpose of building energy efficiency. And later I'll go for the simulation of the ground source heat exchanger by utilizing the data obtained from the previous tracks, the real value obtained from the soil thermal conductivity test and the energy demand from the building energy simulation. Then I'll use the GLHE Pro simulation software for the design and analysis of the ground heat exchangers. In conclusion, soil thermal conductivity is an essential parameter for the estimation of the potential of the soil shallow geothermal energy, and thermal conductivity is heavily dependent on different soil physical parameters and mineralogical contents, and is very site specific. And we can see the variability in the lambda value, thermal conductivity value in the Aveiro and Lisbon soil, and all thermal probes show the similar trends. This research addresses the need for localized data on soil thermal properties to support sustainable energy infrastructure like shallow geothermal energy system. And the accurate and site-specific data on soil properties will be crucial for maximizing the efficiency of geothermal energy system. Thank you so much.
Thank you, Rajendra. Thank you so much for your presentation. So we already passed the time that we had scheduled for this webinar, but we only have time to answer a question that was made in the chat and is for José. So the person found your presentation really interesting and the project at the university. And they are curious about the thermal energy storage. So besides the PCM, did you consider also BTES or ATES, if that's available? And how did you deploy the phase change material, and how much thermal energy did you store approximately? You're muted, José.
Okay, sorry. The first questions are very easy to answer because there is no budget to use different storage for the energy that we can store, but we have no budget. For this, we only use PCM in two ways. The first way is to add PCM to the concrete top layer of the prefabricated hollow core slabs. But the results in terms of energy are good, but not so good for the strength of the concrete. It decays about 45% of the conversive strength. So we do not use it anymore in the concrete. We use in the plasterboard walls and ceilings. And we have a comparative study between two different rooms. The first one with the PCM in the walls and ceilings, and the second one without. And we observed that we can use this PCM storage energy to disconnect the system during the night, because it's a school building, and at the night it's empty. So we disconnect the system during the night, and we use the 5 degrees Celsius of storage in the PCM, in the plasterboard walls and ceilings, to have more temperature in the morning, when we connect the system again. And we saw that these 5 degrees make all the difference, because we have substantial gain in disconnecting the system. I think I answered.
Thank you, José. So unfortunately, we need to finish the webinar for now, but if people that will see the recording after, if you have questions, if you'd like to contact our speakers, please just shoot an email to me or Daniela, and we will forward your questions and we'll put everyone in touch.
Okay, thank you.
Thank you. Thank you, Mafalda. Thank you to all the speakers and for the people who wait until the end of the webinar. So the recording will be available in the next day. I will send an email when it will be ready to the speakers, so you can share it among your contacts. And yes, I had asked a couple of more questions, but maybe I will write you by email for time constraints. But thank you very much. Have a nice evening.
It was a pleasure.
And thank you, Mafalda. Bye.
Bye, everyone. Thank you.
Thank you. Thank you. Bye bye.